Very well. This is May 19, paper 1, time zone 1, question 8. All right, so here's the graph of, and you want to be careful here, this is the graph of the derivative. The curve from 0 to 5, fine. The curve intercepts the x-axis at 1, 0, and 4, 0. So that means that here, f prime of x is equal to 0. F prime of x changes signs, which means your original graph is increasing from here to here, then is decreasing from here to here, and then is increasing from here to here. Because the derivative is positive, then negative, then positive. The derivative has a local min at 3 minus 1. So the local min means that the slope of the derivative at 3 is equal to 0. That will be a point of inflection for our original graph. All right, we want the x-coordinate of the point of inflection. Well, here they're just asking you to recognize the point of inflection on the graph of f. So the x-coordinate is, and here we're just following what it says, is x equals 3. At 3, f prime of x has a local min at x equals 3. That's right here. That means f prime, that means that the second derivative is equal to 0. You can also see that your first derivative prior to 3 is decreasing, and then after 3 is increasing. That means your second derivative would be negative from here to here, and positive from here to here. That means at 3, your second derivative changes signs, which is good, which makes it a point of inflection. Okay. All right, now we move on to B. Find the value of f of 1. Well, in general, the integral of the derivative is equal to the original function plus a constant. So, what can we, the integral from 0 to 1 of f prime of x will equal f of 1 minus f of 0. Now we know that f of 0 equals 3. We're given this. So the other way I can write this is that the integral from 0 to 1 of f prime of x dx is equal to f of 1 minus f of 0. That's from the fundamental theorem of calculus, yes? Mm-hmm. Okay. I'm going to put that in small over there. I'm going to try and rotate it up. Okay. Well, if that's the case, what do we know? We know that f of 0 equals 3. And that's really it. So let's try this. The shaded area, here's the other thing they tell us. They give us information here. The shaded area enclosed by the curve between the x and the y-axis, that means that this right here is equal to 1/2. And this is also equal to the integral from 0 to 1 of f prime x dx. And we just established below, right here, that this is also equal to f of 1 minus f of 0. And f of 0 is given to us as 3. So we can rewrite this as 1/2 equals f of 1 minus 3. Therefore, f of 1 is equal to 1/2 plus 3. 3 is 6 over 2, so that's equal to 7 over 2. So I would say that the value of f of 1 is equal to 7 over 2. And so right here, what we wanted to make sure we had, we read the information, that the shaded area, right here, is equal to 0.5, or 1/2. And then you just need to remember from the fundamental theorem of calculus that the integral from 0 to 1 of the derivative is equal to f of 1 minus f of 0. Right? This would be indefinite integration, and this is definite integration, and it's definite because we've got boundaries on our integral. So now that we have those, let me just kind of erase what we've got except for our result right there. We're going to find the value of f of 4. Now the area enclosed, and again I'm just kind of going with the information that's given. Between 1 and 4 is 2.5. This right here is 2.5, it's 5 over 2. Now, one of the things you want to be careful of is the value, right? The value of the integral from 1 to 4 of f prime of x dx, that'll be a negative value, right? That would be negative because it represents the net change. But the area is the absolute change. The area can't be negative. So the value of f of 4, well, we can use kind of the same idea. So the value of f of 4, I'm going to integrate from 1 to 4 f prime x dx. That's equal to, well, we already know. Sorry. So that'll be equal to f of 4 minus f of 1. And this is equal, they already told us, be careful here, to negative 2.5. The value of the integral is negative. The value of the area is positive. So this integral right here, which represents net change, has a negative value, even though the area is positive. Okay. In much the same process that we had before, f of 4 is equal to minus 5 over 2 plus f of 1, which is equal to negative 5 over 2, pardon me, plus 7 over 2, which is 2 over 2, which is 1. Now, why can that make sense? What that's telling us is our original function was increasing from 0 to 1. It went up. Not a whole lot. If it started at 3 and it ended up at 7 over 2, it went up by 1/2. That was the value of this area. Then it went down by 5/2. So we were at 3. We ended up at 3.5. We went down 2.5. And at 4, we ended at 1. The useful thing here is now they're asking us to sketch this curve. Clearly the coordinates of the maximum and the minimum points. Okay, well, right here, at these zeros, that's where you've got a maximum or a minimum. When the derivative goes from positive to negative, you've got a max. From negative to positive, you've got a min. So right here, I'm gonna do the same thing. I'm gonna erase this, and I'm now gonna sketch f of x. We're gonna delete this. And for f of x, what do we have? F of 0 is 3. We found f of 1, which was 3.5. So this is going to be an approximate sketch, right? We found f of 4, which was 1. This is 4 comma 1. This is 1 comma 3.5. What else do we know? We know that there's a point of inflection at 3. And that the derivative, the slope of the derivative at 3 is minus 1. So minus 1 goes down approximately like this, so like this, something like that. So I'm gonna, whoop, and then it goes back up because my derivative is increasing. Do I have any other intercepts? I'm gonna make sure I label these clearly indicate the coordinates. So this is 0, 3. And I think that's all we can really, I would make this a little cleaner. And we have to indicate the max and the min, and I think that's reasonable enough. If I were you, I'd make sure that this graph right here, when you're doing this for your IB, is a little cleaner, because this is not a very explicit min. So can I erase this without doing, I erased my whole graph. That's fine. All right. It's not a work of art, but it does say sketch. We don't have any explicit y-intercepts that don't make any sense, and that represents the areas. So this was really a question about the relationship between the derivative, the area represented, the change represented by the area, and this C right here was about the distinction between the value of the integral and the value of the area. Any questions?
Can we, another way to solve this problem is to with the data, with the things that we have on the graph, first we rewrite down the formula of the graph?
Well, you could try, but I'm not sure how we'd find the formula of the original function, because we don't have much. So it looks, based on this right here, based on our function, on our graph, it looks like this might be, what, conceivably a cubic function, but it could be almost any other function, right? Our original function could be some sort of transformed cosine graph. It could be, because we only have this from 0 to 5. So we're not given a whole lot of information to find the original function. We're mostly given values and points.